Quantum Foam. Episode 30. Quantum Computing.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
today we are closing up this section of 10 episodes. The third section of 10. This is episode 30. We are discussing quantum computing, the entire reason for what we're doing here, the way that we're going to test our theory, the way we are going to prove my theory. So this is in tune with topics that I've been going through. The last close of 10 episodes was quantum mechanics, pretty hard quantum stuff that nobody understands. Not even you, not even Richard Feynman, not even me, not even somebody. There are people that understand a subset of it, but if we can come up with a way to organize this stuff into a standard model that everybody can sort of understand, and even if it takes getting a PhD to be said that you understand it, which it should not, you do have to weed out the quacks from the people who are doing real science, and sometimes some of them even slip through. So let's not all pretend like we don't have one of those around the office. Yet occasionally they have their uses, but that is neither here nor there. Let's get into this. The way we are going to prove my theory. First and foremost, this ability to quantum compute at a high rate of speed will crack all current encryption on the planet. I wouldn't say all forever, but other types, public key. I gotta be honest, to even explain this stuff to you, you have to know what you're talking about. So yes, lots of this stuff is straight up from the internet that you can all read, but we all know that when all of you go through that and you're like, you just quit at some point. Let us see if we can have quantum supremacy. What? Quantum supremacy.
Google supposedly has quantum supremacy over others with their 54-qubit quantum computer.
It's called the Sycamore.
Maybe we can talk about that later on.
IBM has one too.
I mean, these kind of go back to the Turing machines. What do you know about those? I read the books about cryptography and about the first computers and about all of that. If you're interested in that, go look it up. But what I'm interested in now is actual quantum computers utilizing qubits and more than likely using the prevailing model of quantum computation using quantum logic gates. We understand normal logic gates based off of linear computers, so quantum logic gates are the same thing, except we're dealing with probability vectors here, density operators. We may represent the state with different types of math here. We can use Dirac notation. Remember the bra-ket notation? It's pretty ubiquitous, right? So people like to use it. I don't fully like it, just like I don't fully like Newton's.
Really? Bugger off.
Or Leibniz, or Einstein.
Your notation looks a lot like mine, there, young laddie.
Or Schrödinger, or any of those motherfuckers' notation. Some of that's like, woo, a squiggly wiggly, what? Go away. We need something better than this bullshit. Nobody gets it. It's not meant to be kept from people anymore, okay? So it needs to just be descriptive enough for a high schooler to pick it out. We were trying to learn this stuff in high school, and they wouldn't even let us go above anything besides stuff I was going over this section of 10. The vector stuff. That's actually pretty advanced for 16, 17-year-old. But they wouldn't go in anything above that. But that's the first thing you do in Physics 1 anyway. Getting a handle on going in and out of events before, during, after, figuring out calculations and problems that are multiple steps and things like that to solve mechanics problems, which is simple vector addition and subtraction and multiplication and cross product and dot product stuff. Remember these cross products. There's a point that they give you, it's perpendicular to part of something. It's like skipping a step kind of thing. It's a trick to figure out different things with orientation of 3D objects.
So this is pretty much needed when doing various mathematical transformations. The orientation of the shape or object that we are interested in after it has gone through a series of equations which will determine its new position on a Cartesian grid lattice.
pretty much
Cartesian graphs. This is the standard grid that we superimpose various equations upon.
kind of important to make sure you get your P's and Q's and T's and X's and Z's and whatever else. It's more than crossing T's and dotting I's. Lots of matrix multiplication. You know, a 3 by 5 grid times or dot a 3 grid by a 4 grid actually equals a different grid altogether. So the size and the scopes of these point matrices can grow in length and width infinitely. They can grow to infinitely many factorization complex numbers. So you're dealing with the alpha beta bullshit, blah, blah, blah. We don't want to get too far into the matrix math that runs this stuff, blah, blah, blah. But essentially what makes a quantum computer different than a normal computer is that in a normal linear computer, they have a on-off state, 1, 2. In a quantum computer, they have an on middle or on-off middle, blah, blah, blah. On-off, blah. The qubit, they have a variable that can be on and off. The qubit, the structure that hides within that in your programming is everything.
That is your version of the quantum computer, not what others are doing. Not exactly. Let us ask Mr. Stephen Hawking.
Sure thing, Mr. Einstein. The way that computer binary digits work when put in and out of calculations is quite complicated indeed. The way our host here is describing these qubits is just another take on the fundamentals of quantum computing. 3 different options can also be seen as 4 different options, with one of them in the middle consisting of 2 simultaneous values, or the 2 on the side having the same 2 options, which is 4 things that can have 3 options and a direction. The specifics of the logic really doesn't matter here because we are not actually programming a computer at the moment. Let's just get back into describing the traditional computational mathematics.
Everything beyond your traditional computational mathematics. This is the split between the 1 and the 0. The 1 does this, the 0 does that. But then what does the X variable within the little box that's a qubit signify? What does that middle one signify? Well, you can put it at the end, middle, or the beginning. But I like visualizing it like being in the middle. You could do on, off. You got your 1 on the left, you got your X in the middle, you got your 0 on the right. What can it be? Might as well signify it as that. So that is the split between the 0th bit. That is the idea behind that.
Somebody has to make the first qubit.
So normally computer programming is based off computer binary. That is on and off. But remember, this quantum computing has an on, off, and a variable. The secret behind this is that in that variable, it has the ability to be exactly 50% even on one direction and 50% even on the other, based on the direction of a certain subset of programming. So if you have a positive or negative, it goes that direction. They go over some of these in this quantum computing. There are different types. That one would be a one-way quantum computer. It prepares an entangled resource state and then performs a single qubit measurement. It's one way because the original resource state is destroyed upon measuring. This can be modeled to measure a electron or something that you have to ruin the state while you're measuring it. So that can be helpful for that.
That's right. They use things like the electrons from phosphorus lined up in an electric field. If the electron is in the ground state, it is said to be in a spin-down state, and the qubit is counted as off. The ground state means that the orientation of the electron is at the base level. When it has spun around and is in a spin-up state, which takes energy, the qubit is counted as on.
There's Adiabatic Quantum Computing, AQC. It relies on this adiabatic theorem, and don't really like that much. Look into that if you want. There's a little bit more grounding in the quantum Turing machine. You could call it a universal quantum computer. Remember, the original computing was built off Turing machines, and these were a way of counting the decimals mathematically in an infinite way that can reuse electronics to actually do the calculations. So essentially, it's built right into the architecture of everything that there already is. So that is more than likely a good one to start on as well. Its model is rather simple, but it is what it is. It doesn't need to be any more complicated than that. So
the traditional way to count qubits is they actually really have 4 possible values instead of just 2, as in traditional computing, what you would call linear computing. But the other 2 quantum values really can be places within a variable, say an X in the middle, and programming applied. This models the 4 variables the same way as the traditional methods of quantum computing. I wouldn't be surprised if this is exactly how Google does in fact program their quantum computer.
you could go into this, you could go into that. You could go into quantum circuit model types of quantum computing, more stuff from information theory. So this deals with sequences of quantum gates, which are reversible transformations. So they're using an n-bit register. Each bit could be 1,000,000 bits within the bit register. It could be an n-qubit register. We use n-bit registers in normal computing, so this would be an n-qubit register quantum circuit model. So that has a little bit more potential. We will probably be pulling some stuff out of that one. The thing is, these aren't even really that comprehensive. They don't even make any sense, and nobody's really testing too many of them. IBM and Switzerland is testing this shit, but they may be having some cooling problems and other problems, but
I'm pretty sure they know what they are doing. They started working on quantum computers even before Google.
we are building normal silicon with the ability to interact with entangled particles using a superposition within the programming and actually using quantum mechanics within the programming with normal linear computers. So our supposed quantum computers are just going to be slight extensions to the silicon that we already have. So the silicon probably isn't going away anytime soon because we are going to need to have circuitry and electronics and materials that can connect to the other end of the electronics that deal with the quantum qubit portions and where the quote-unquote imaginary complex math will take place. So our supposed quantum computers are just going to be slight extensions to the silicon that we already have. Remember, in normal math, we already have imaginary numbers. So it is not hard to create an imaginary structure for the purpose of a new type of calculation. Paul Benioff helped pioneer the field. So you got to start somewhere. Information theory, 70s and 80s. They're involved with helping computers actually come to be in the first place. Turing Machine. Of course, Richard Feynman, he built all those diagrams for everybody. You'd think it's standard, but damn, this stuff gets so complicated that it's like all these directions and all these wiggles of lines. What is going on? What particles are coming out of nothing and what isn't? If you've seen some of this actual quantum mechanics using the notations that people generally use, that's what it looks like. That's what makes a whole chalkboard or dry erase board or computer board or paper or tablet or whichever look like it's filled with Greek and numbers intermixed with bullshit, because that's essentially what it is. But there are other things with this that are interesting. We can go above it and look at quantum information science. Quantum computing would be within this. This deals with some of the stuff that we are interested in. Of course, quantum teleportation, quantum entanglement, etc., etc. So we went over this in the first section of 10. We want to know how to actually teleport things. So we want to control the teleportation of quantum information being transmitted from one location spatiotemporally to another. We want to control. This stuff is cool to us. So when particles are entangled, you generate a pair of particles and they share a spatial proximity, and then they get entangled with one another because they are part of something else. And so their upspin on one might be the downspin on the other, or something inverse and opposite or such, in which case they are entangled.
We are getting to the stuff about faster than light communication. There are experimental physicists that are successfully interacting with antiparticles on silicon microchips now. Very exciting stuff.
But keep in mind there are other things like gravity and mass that retangles things that are entangled. So that is one issue that might arise if we try to build faster than light communication beyond the planet.
So, decoherence is always wanting to affect the particle and antiparticle pair. Got it?
Now, the first goal is to tackle faster than light communication on the planet. And we might find a way to do it if we can deal with these gravitational waves and gravitons to deal with everything correctly. And I just don't think that people are accurate enough in their physics. So I am trying to up the accuracy to a point to where we can program the universe. And it's only going to be a small subset of that, unfortunately, because that's the way it is. So obviously quantum cryptography has already been commercialized. They got things like a one-time pad, but these things only have limited uses. We might want to know what a qubit is. How is that different from a bit? A quantum bit. It's a basic unit of quantum information. These qubits have more than one state. They say two-state or two-level, and however you describe this does not exactly matter, but a two-state system does not exactly matter. matter, a system that can exist in any quantum superposition of two states.
We're gonna have to go into more detail.
Two states. Two states.
The models get quite specific and confusing. Right now, though, we need to take a quick break.
Obviously, this is the midpoint of episode 30, Quantum Computing of Quantum Foam. Quantum foam.
Go on, Newton, ask away. I am just as interested as you are.
You know how I am very well versed in the math I created, right? This new math involving higher spatial dimensions, it just doesn't make sense that you can model such a thing that just simply can't exist.
Remember, we can use can't exist types of maths and spaces and grids and lattices. Let's use a Hilbert space to describe this system that only has two dimensions. So it's a two-dimensional system that adheres to the mathematics included within a Hilbert space, and it can describe this space. But it's how you describe it, like we were going through earlier, which I think is far more intuitive. You have your on, your 1 on the left. You have your off, your 0 on the right. And you have your x in the middle off to the side to make a triangle. It is essentially a 50% difference engine that has programming that directs it to a certain direction that begins, depending on the quantum system, with either a 1 or a 0, a left or a right. The electrical energy, each electron starts going through the wires to the first logic gate, which is in an on position, then off, then on, then off, whatever kind of combination that there is. A two-state system is the same thing as looking at an x in the middle, a left being an on-off, and a right being an on-off. So this covers, in quantum mechanics, this two-state system covering two dimensions using a Hilbert space to describe it, all the way up to the string theory, all the way up. So that can definitely be modeled in the exact same way that is within here. Theoretical physicists coined the term. So Shoemaker, founders of quantum information theory, Benjamin Shoemaker, William Wouters, Paul Benioff, Peter Shor, Yuri Manin, lots of different people that can be said to be involved with the creation of this theory. Remember, this is built upon the quantum mechanics and other such science that was done as well. So the information science was also built upon that. Linear computer technology was built upon this, as well as quantum computing technology. So remember, binary digits characterized as 0 and 1. That's what we've been saying. 1 on the left, 0 on the right. This is said to be within information entropy. It's just the basic quantity associated to a variable, random variable. This is going a step further, proving how much is uncertain within each of your variables. 1 is on, 0 is off. That is enough said there, I say. The other stuff that we have here, we are talking now between quantum and linear stuff. A quantum state of a qubit can be represented by a linear superposition of its two orthonormal basis states. They're basis vectors. You're beginning with a problem, you have two vectors, you got one, you got another. These are the basis vectors. They can be noted as bracket 1 and 0, a 1-2 grid, 1 column, 2 rows, 1 on top, 0 on bottom, and then the opposite of that.
Orthonormal basis states.
You could be using the Dirac notation, but in order to communicate with those that need to be communicated with, I'll more than likely be forced to use this Dirac notation, bracket notation, but we will see what looks good on a piece of paper.
One last thing, to help everyone understand all this. Okay, so you are talking about these two states for the qubits in quantum computing, right? So, what this actually means is two values that are 2 to the n. So, the first value of n after 1 is obviously 2. So 2 to the 2, which is 4. That is where they get the 4 values instead of 2, like merely on and off. So these 4 values come from a 2 to the n qubit that can then be modeled as an on, an x variable, and an off. This may be one of the only ways to do it.
So a qubit state. So we have different states here. You have things called a Bloch sphere, B-L-O-C-H sphere. It's a geometrical representation of the pure state of a two-level quantum mechanical system. Qubits named after the French physicist Félix Bloch. So within this sphere, the probability amplitudes for the superposition states are given by alpha is equal to cosine theta over 2 and beta is equal to e to the I psi sine theta over 2. Remember, we got to do some stuff with that I psi stuff. The I is imaginary. The psi is your imaginary variable. So we're trying to find our unknown variable here. So obviously the point of having this sphere is because we can do sphere mathematics, but the surface of this Bloch sphere is a two-dimensional space. So it just represents the state space of this pure qubit state. It's a state space. It's an abstract space. Just come up with a model to talk about something. An abstract space where different positions are represented, not literal locations, but sort of a position in a mechanics. Remember, a spinor, that is something that describes lots of things in loop quantum gravity. We're not versed enough with that to describe that correctly yet. But for now, just know that a state space is something that represents positions that aren't literal locations. Similar to the spin of a particle. Graviton, spin 2, spins around twice on this theoretical spin space state. So just know that a state space is something that can describe something that's abstract, that talks about states of quantum phenomena.
These state spaces can get really complicated because of the nature of quantum computers. Let's say that we want to build a quantum computer that is theoretically faster than Sycamore from Google, faster than Paris from IBM, the next fastest computer that also has completely new operating instructions that are more efficient than those that have been developed so far. They have only been doing this for a few years now. You have been doing it for many, but it is about time for you to lay down your plans for everyone and to begin actually experimenting in the lab instead of on paper. We need a smooth transition into the age of quantum computing and not one where everybody's encryption is being cracked.
Within these state spaces, there are two local degrees of freedom.
Encryption is being cracked.
Phi and theta. Phi, 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 and theta. Some of them can be referred to as being in mixed states, but it really depends on what you're doing here. I was just trying to describe the representation of a Bloch sphere, which uses this notation stuff that they used back then, but it's a little bit jargony for me. We will have a better notation during the proofs when they are written up. When the final copies of these proofs are written up, I have a lot of fact checking to do. There's a lot to be checked in this. What if I find out this is all bullshit? Well, it'll be a lot of entertaining bullshit then, but I'm pretty sure I am onto something big here, and everybody says this, so I don't need to really say it. I just need to show it and prove it. The eye is up in the sky, fully operating. I can measure the gravitational influence that is going to be happening.
The James Webb Space Telescope is currently at the L2 Lagrange point on the other side of the moon.
What applications can we do? Super dense coding. It's a way to transmit 2 classical bits. It's like sending 1 qubit from Alice to Bob, under the assumption that Alice and Bob are pre-sharing an entangled state. So these are good ideas, and we will definitely be integrating these into plenty of programming environments that will be created in the future and that have already been created. What are the implications of this? You can look at stuff, but these are the people at the National Institute of Scientific Research. They're finding things in 2017. It's in Quebec. They produce your labists, your experimentalists. They give you your laboratory science. So they constructed a pair of qudits. They constructed a pair of qudits with 10 different states each, giving more computational power than 6 qubits. Damn it. I just thought of this last night, and they did this 3 years ago. Well, I think they're onto something, and so am I.
I'm not sure if it would be easier to use more superpositions or not. It really doesn't matter what you call your rows and what you call your columns. Quantum computing is done differently than classical computers. You write a function that solves an equation using the old computers. Using new quantum computers using qubits, you have to already know the answer to your inquiry, but that just gives you the ability to write programming that will solve your equation during the qubit-to-qubit operations. So it is somewhat backwards, or inverse. There are many ways to build these things, as you have already been going through.
Those really are some good insights, Mr. Hawking.
Thanks, Sir Isaac.
And so, I'm not going to call it a qubit. It's still a fucking qubit, okay? But the qubit is arranged the way I have described it. 1 on the left, x in the middle, 0 on the right. They're all separate variable locations, so they don't have to be on the left or right or up or down. Just 1 as 1 relates to x and or 0, 0 as it relates to 1 and or x, and x as it relates to 0 and or 1. So logically, they can be superimposed on a logical representation grid. What I said is they can be switched around left, right, up, down. It doesn't matter. So let's not go crazy calling everything qubits, qubits, woobits, whatever it is. No, there's a bit and there's a qubit. Whatever it is, that's it. Whatever it is. If you cannot qubit, then you must bit. If you cannot bit, then you must qubit. That's it. There you go. That one.
LOL, OJ.
Describe your nuclear spin however you want. I have electronic spins to describe, and there are other Fock states. No, for real, that's a thing. A Fock state is a number state. It's a quantum state that is an element of a Fock space with a well-defined number of particles. These states are named after the Soviet physicist Vladimir Fock. Fock states play an important role in the second quantization formulation of quantum mechanics. I think they're talking about stuff with like puissance or Laplace.
What is wrong with you?
What Fock state are you talking about?
Be serious.
What fucking state are you talking about?
There you go again. Messing around right on set. Oh well, I guess it really has been one hell of a ride so far. We are almost 30 episodes in. This podcast is really coming together.
That it is.
Hell yeah, it is.
You have been working on everything and much else for a lot of this year. During all the changes in the world and throughout this pandemic, you started recording before everyone else that decided to start this year. But that doesn't really matter. This is about science, not politics, not medicine, mostly math, physics, computers, and other science fiction-styled phenomena. I hope we can actually make it to 1,000 episodes.
We all do.
Yes.
Time-bending code. Time-bin encoding. What time-bin encoding are you going to use for your time-bend code? That's a toughie. So, topological systems. The braiding of excitations. So what does this stuff do? These things can be described with qubits and bits. Qubits with 1 zeros and x's. So nobody really knows how to build this stuff until they do, because why do you need the 50% difference engine? Because the computers don't know how to do it otherwise. This is the way around it. This has to be built into the computers. The reason why we haven't made robots yet.
You mean, why we have not made robots that are actually indistinguishable from human intelligence yet?
Is because it's too hard to do with linear computers. Now, we're able to manipulate the AI in terms of describing logical information. That took a long time to be able to do. But now that we're able to logically describe English and other languages using logical, usable mathematics, it can be put into the new types of computers that will give it the life it needs to actually run and emulate intelligence in the form of real artificial intelligence that we can trust with the lives of humans and other such things in the architecture and infrastructure of the cities on our planet. Because what happens if the planet just gets fucked somehow? Then what? Right now we are. If you want to be warping any time in the next 100 years, you better pay attention to this quantum computing, the implications, the implementations that are already here, the new physical implementations that will be created based on new information that is and has been disseminated to you. Figure it out. If you have questions, send them. If you're talking about oranges, let's talk about oranges. If you're talking about the superconducting phase qubits, then let's talk about the stupid ass superconducting phase qubits and the stupid ass motherfucking superconducting flux qubits, okay?
I've also greatly enjoyed playing on the podcast so far. I like the idea that we can go into detail on basically anything right here on set, whether others are following along with paper or in their heads. We got what you need, of all the brain teasers. This quantum computing, this is the whole point of trying to figure out the theory of everything, so we can build quantum computers that will actually be able to keep up with humans.
Yes, what an idea. Quantum Foam, the podcast. Very enjoyable, hard to keep up with, but a lot of folks only have time to listen to radio programs and the like while working with their hands, while exercising, or working at a job of some kind. This sort of thing keeps the mind busy.
Sounds like a plan. But for now, sounds like a plan. That is it for episode 30, Quantum Computing of Quantum Foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.